of our vertical heterojunction photodetector. So MOS2, large area MOS2 was grown on SiO2 substrate. On top of it, we deposit our perovskite nanocrystal. So basically, this MOS2 layer has a very high carrier mobility. It's a 2D monolayer, so it has very high carrier mobility, and this perovskite nanocrystal has very good absorbance. So this perovskite nanocrystal absorb the light and harvest that light, and it produce electron and hole pairs, and these electrons are further transferred to MOS2 and collected in electrode, which gives high photocurrent of the device. So as it is a vertical heterojunction, one electrode is connected to our perovskite nanocrystal field and another electrode is connected to underlying MOS2. So next one shows the UV visible absorption spectra of pristine cesium lead bromide field, bare MOS2, and the composite MOS2 cesium lead bromide film. So you can see in case of composite film, absorbance was significantly improved due to the co-absorption by both the system. So this high absorbance results in the high photocurrent of the device and good detection performance. So in case of PL, photoluminescence, we observed in the heterostructure film, the PL was decreased compared to bare cesium lead bromide film. This is due to possibly due to the charge transfer, photogenerated charge transfer from cesium lead bromide to MOS2, which reduce the radiative recombination. Though the PL intensity quench, we observed this TRPL decay become faster, which also confirms the photogenerated carrier transfer from cesium lead bromide to MOS2. Further, this carrier transform was proved by Raman measurement. So this is the Raman. These two are the Raman of bare MOS2 and MOS2 cesium lead bromide heterojunction. So in case of hybrid structure, the A1G peak related to MOS2 was shifted towards lower this wave number inverse. So this shift is due to the end doping in MOS2 due to the charge transfer from cesium lead bromide to MOS2. Further, we studied the performance of our heterojunction photodetector. So first one shows the IV characteristics of our heterojunction photodetector. So this black one is under dark condition, and under light the photocurrent was increased significantly, and you can see under reverse bias this increment of photocurrent is much higher. As reverse bias, this band bending occurs, and this charge suitably transferred from cesium lead bromide to MOS2, so under reverse bias the photocurrent is much higher. The linear dynamic range of this photodetector shows that it can detect over a very large scale of light intensity. And next one shows the photoresponsivity of bare MOS2 and the hybrid photodetector. In case of hybrid photodetector, you can see the responsivity is much higher due to this high absorbance and suitable carrier separation, suppressing the radiative recombination in cesium lead bromide, and this responsivity matches with the absorbance of bare cesium lead bromide. Thus, this responsivity mainly comes from this perovskite nanocrystal. And we observe very high responsivity of 6.7 ampere per watt at 400 nanometer of the heterojunction photodetector, and this photodetector exhibit very ultra fast photoresponse due to the fast carrier transfer to 4 microsecond current in the heterojunction photodetector. Further, we studied the mechanism of our photodetector by Kelvin probe force microscopy. So we studied the work function of this MOS2 and heterostructure film. So from work function calculation, we observed for monolayer MOS2 work function is about minus 4.3 electron volt, where in heterostructure 4.2 electron volt. So this MOS2 and cesium lead bromide is forming a type 2 semiconductor heterojunction. So this semiconductor type 2 heterojunction helps in suitable carrier separation from perovskite to MOS2. So further, we have studied the electronic structure calculation and charge transfer mechanism. So these are the DFT based density of states calculation of bare cesium lead bromide, MOS2 and heterostructure. So from density of state, we observe it is forming a type 2 heterojunction, and a significant amount of charge is transferring from cesium lead bromide to MOS2, which enhance the performance of the photodetection. So highlights of this work: we have successfully grown all-in-onoric cesium lead halide nanocrystal, and we also fabricate down-converted high-performance LED, and this we further fabricate 2D monolayer MOS2 cesium lead bromide vertical heterojunction type 2 photodetector with responsivity which is significantly high, 6.7 ampere per watt, and response speed of few microsecond. And further we studied the mechanism of the high performance photodetector by DFT and Kelvin probe force microscopy. Thank you for your kind attention.
Thank you very much, Dr. Jyotir. Now I'll ask audience to ask questions. You have. Yeah.
I have only one query. Can I
Yes,
ask?
sir. Yes, sir.
This quantum yield, how did you estimate from photoluminescence?
So actually, we estimate quantum yield by normalizing the absorbance. So we have an integrating sphere with our photoluminescence measurement setup. So by this integrating sphere, we normalize the absorbance, and then we calculate the absolute quantum yield.
Normalized with respect to what?
So we have standard sample. So we know the value of this like rhodamine B6B or
Okay.
something. This so from this standard sample we normalize it and we calculate.
Right. Very good.
Yeah. Professor Giri.
Hello? Yeah,
Yeah.
yeah. So I wanted to know, Jagdeep,
Yes, sir.
your response of the photodetector is not so broad.
Yes,
It's
sir.
over narrow range. So how can
Yes,
you
sir.
broaden the response
So
that
actually,
is to
yeah.
red and beyond red region?
Yes, sir.
Do
So
you have some composition which can take to the broader range?
yes, sir. Yes, sir. So this perovskite nanocrystal, we can tune this absorbance. So if we take iodine-based some nanocrystal, it can detect light up to 800 nanometer like that. So by tuning this nanocrystal, we can tune the range of this responsivity, spectral responsivity of the device.
How much? Maximum how much you can tune?
780 to 800 nanometer for this perovskite nanocrystal, or beyond that we have to give some infrared detecting nanocrystal like lead sulfide or lead selenide like that.
Oh, thank you.
Thank you, sir.
Okay, Jaideep, I have a question. See, this
Yes,
response time is roughly about 40 microseconds, no?
Yes, sir. Yes, sir.
Would that be considered as slow in general?
No, sir. This is very fast. Means for normal semiconductor, this silicon-based semiconductor, typically it gives this microsecond region. Sorry, millisecond region. So this due to this MOS2 film, it shows very fast response.
Okay. Right. All right. Giri, you have some more?
Yeah,
Yes.
one comment.
Yes, sir.
This silicon response is silicon detector, standard detector response is always microsecond. The perovskites are very slow. That's why you will get millisecond. But because
Yes,
of MOS2, you are getting microsecond. Perovskite is slow, not silicon.
Yes, yes,
Okay.
Okay. All right. So if there are no further questions, then let us thank Jaideep for his great talk. Now our next speaker is Jyotir Maybora. He is pursuing his doctoral studies with Professor Bhuya and has been here since 2018. and he has been awarded Best Poster Award in 2 consecutive years, one in Frontiers of High Energy Physics in Hyderabad University, and the other one was in DAE Symposium last year, which was organized by Naisar Bhubaneswar. And Jyotirmay today is going to talk about his title of his talk is Rare Decay Processes Using the Bell Detector. So, Jyotirmay, can you take over now? Yeah.
Yes, sir. Thank you. So let me share my screen.
Yeah.
Can you see my screen now?
Yes, yes.
Yeah. So, good afternoon, everybody. So my name is Jyotir Maybora, and I'm a PhD student working under the supervision of Professor Vipul Bhia sir. So at the outset, I'd like to thank our organizer for giving me a chance to speak on the eve of National Science Day. Thanks a lot. And the topic for today's presentation is search for rare decay processes using the Bell detector. So the Bell detector is synonymous to saying that it's a Bell experiment. So how it's different from the other detector is that the Bell detector is essentially a luminosity frontier detector, contrary to the energy frontier detectors such as the LHCBs. So the Bell detector or the Bell experiment, so the prime are being and see the observables within the standard model or beyond the standard model physics. So today my presentation will be on the Bell detector, and the talk is divided into 5 sections. So I shall briefly describe what is standard model, and then quickly go to the need for flavor physics, or we can say the different aspects of flavor physics. And then I shall talk about the BS sector, the area where this is the broad area where. And I shall specifically speak about the B sub S to rho 0 pi 0, which is one of my PhD topics, and then summarize about the presentation that I have made. So let's begin. I'm on slide number 2, standard model and flavor physics. So onto my left, I have the figure which depicts the fundamental particles. So it essentially the fundamental particles are divided into 2 groups. One is fermions and one is the bosons. So we will first come to the boson.
Excuse me. Okay.
Yes.
No. For me, the slides weren't changing, but now they are. So it's okay. Sorry.
Okay,
Sorry to interrupt.
Okay, fine. Yeah. Then we have this boson, so which are the mediators of the fundamental interactions. So we have strong, electromagnetic, weak, and the gravitational being very feeble with respect to the strong, electromagnetic, and weak. These are somewhat neglected in particle physics. So that is why it's not a theory. So at some point in time, gravitational forces will need to have to be included within this area. And then we have, coming to the fundamental particles, we have the divided into leptons and quarks. The quarks, which are shown in up, down, charm, strain, and top, bottom. So they can experience forces such as strong force, electromagnetic force, and the weak force. Whereas the leptons, which is devoid of a quantum number, they cannot. Bottom quark can form a bound state is that the top quark, which is the heaviest quark of roughly 174 GeVs. So the lifetime of the top quark is very small or very short, roughly of the order of 10 to the power minus 25 seconds. So it does not have enough sufficient time to form a bound state, and it is why B quark is the only 3rd generation of quark which can form a bound state. Now, as you can see below in the table, I have shown some of the experiments. So we see that corresponding to each of the transitions, there is an experiments, more than one, sometimes are being devised to study those interactions and know their properties. The one that I will be mostly concerned is about the Bell and Bell 2, because I deal with those. And we see that the Bell and Bell 2 experiments deals with the charm going to a down quark and a strange quark type of interactions, and the bottom going to an up quark and a charm type of interactions, and together with the top going to down and strange And these are all the bottom, the top going to down and strange. I will speak about this. These are loops that how new physics are associated with these loops. I will speak in a while. So this table shows how experiments, or what are the different kind of experiments that are being designed to just move interactions among the fundamental particles. So let's move to the next slide. Slide number 3, need for flavor physics. So the flavor physics program essentially is contained in the CKM matrix. So the CKM matrix is named after 3 scientists, the Kabibo, Kobayashi, Masukawa. So they proposed, especially the first was proposed by, in 2D case was proposed by Kabibo, and later on Kobayashi and Masukawa extended that 2D scenario to 3D scenario, and we have this corresponding to the 3 generations of the quarks. We have the CKM matrix, and in the CKM matrix essentially tells us about the transition probability of the different transitions among the different generations of the quarks. And experiments, these elements can only be determined experimentally. So now in order to perform phenomenological studies, so this matrix has been first parameterized by Wolfenstein in 1972. So and we see there are different parameters. So this Wolfenstein parameterization is essentially expanded in terms of lambda. The definitions are here, lambda, a lambda squared rho plus eta. And we see that in the Wolfenstein parameterization, if we are all aware of the matter-antimatter asymmetry in the universe, and the contribution, the only contribution that can be contributed from the quark sector comes from these 2 off-diagonal terms, essentially because it is a complex term. These 2 terms are complex, and this is the only source of CP violation within the quark sector. Similarly, from the lepton sector, we have that can come from the PMNS matrix as well. Similar to the VCKM, we have PMNS matrix in the lepton sector. We are dealing here with quarks for the time being. And these are the only CP violation term within the standard model. Now, the VCKM matrix has a very important property, is that it is a unitary, that is VV dagger is identity. Now, if we expand it, we will get 3 sets of equations. And one of those sets can be actually represented in terms of a triangle. There are different sides of the triangle, the angles of the triangle, and the area of the triangle give us important information about the various interactions. So all of the flavor physics program, the ones that deal with the CKM matrix, is destined to find out the sides of the triangle, angles, and the area. And it is also important that the area of the triangle is proportional to the CP asymmetry. So greater the triangle, area of the triangle, so greater the CP asymmetry. And all of the experiments which deals with the flavor physics, they work in determining precisely the values of the triangles and the angles of the triangles. And we have this VCKM matrix where I have shown the different transition matrix elements, and together with the decay channels, which through which we can actually measure them precisely, are mentioned here. The ones I have not shown do not come from the Bell and Babar. Bell to or Babar. Babar is also a similar kind of experiment like Bell. And the whole the aim of the flavor physics program here is that we are to overconstrain the unitarity triangle to precisely measure the CKM matrix elements. And these measurements are already in the precision, so we need more and more data to overconstrain the triangle. Now there is another aspect of flavor physics. So this one is regarding the CKM matrix. The another one is regarding in search for the new physics. So this is the area that I work on. And on the diagram shows the different transitions, the strength of the transitions among the different quark generations. And as a rule of thumb, we can just remember that the intra generations transitions have more strength than the intergeneration transitions. As we can see, the black line, the solid black line, has a strength of 1, the relative strength of 1, and similarly the others are determined according to that one. And we have processes such as the loop level processes, which are also called the FCNC processes. Why these are FCNC? Because these are flavor changing neutral current process. For example, if we look into this Feynman diagram, say one of the decay channels, say surface to Feynman, and on the initial state we have a B bar S, and on the final we have an S bar. Now B going to an S, if we look into the charge content of of the B and the S. This is just the spectator quark, so this does not play any role. So the important quarks that play an important role in this analysis is channel B and S here. So if you look into the charge of the B and the S, they are almost they're exactly same. That is plus 1/3 B bar S bar. So with the charge is not changing, but there has been this type of processes are called FCNC processes. However, these processes are suppressed within the standard model by a mechanism developed by 3 scientists, GIM. And these processes can only occur via loop level processes. And as we can see, this is a loop level, this is a loop, and it is being mediated by the top quark. But we know that the bottom cannot go to a top quark because the top quark mass is very, very heavy. But these are all virtual processes. So in a virtual process, and or particles can enter this loop, and if new particles or physics enter this loop, then there will be a change. There can be a change in the Brunson fraction, and on measurement, if you find discrepancy or a disparity between the prediction and the measurement, then we can at least say that there is some new physics, and then we can hand over that to the LHCb. What is the exact particle? Because they deal with the energy spectrum, they can definitely find out the particle. We can estimate the discrepancy between the theoretical measurements. Similarly, we have the B sub gamma gamma. This is also a FCNC process, and these FCNC processes are important for going beyond the standard model. One of the famous loop level process that paved the discovery of the charm quark is case to mu plus mu minus. So this is one of the diagrams where GIM proposed the new quark, that is a charm quark, and the loop level process is very important. So the summary of this slide is that the rare decay processes are very important ones to go beyond the standard model, and the BS and the BD sector can offer plenty of opportunities to study the new physics. If we want to go for search for new physics, the BS and BD sector are plenty of those. So we move to the next slide. So this is a broad area where I work, a piece of S sector, and and then we have the production mechanism. How do we produce the B sub S in E plus E minus colliders, just like Bell or Bell 2? So the important point is the production mechanism is very important, because depending on the production mechanism, it actually determines the amount of background that we will have in the experiment. In PP collisions such as in LHC, the background level is very high than E plus E minus collisions. So in E plus E minus colliders such as the Bell experiment, we have this E plus E minus going to an epsilon 5s. This is again a resonance state of BB bar quark. It has a very short lifetime, roughly of the order of 10 to the minus 17 seconds, and it quickly decays after production to B sub S star and N to B sub S star, and the B sub S star decays to B sub S and gamma. And this is from where we study our analysis, from where our analysis begins. The B sub S can go for varieties of decay channels, and we choose one of those to study. So on my left, we have this hadronic events, the different kind of hadronic events at epsilon 5s resonance. It is not that at E plus E minus, at a center of mass energy of 10.86 GeV, only epsilon 5s is produced, or only the B sub S is produced. There are different BD processes as well, so that will be a background for the B sub S, the target sample that we are working on. So these are some of the backgrounds. That we have the UDSC continuum, we have the non-BSBS type of decays, and we have contamination from other decays. For example, if I am working on say B sub S to rho 0 pi 0, then the contamination will be from B sub S to pi 0 pi 0. So this type of decays are also, we also have to negate those contamination from other B sub S decays as well. And this is a diagram, the cross section, the hadronic cross diagram, so which shows a figure which shows the different cross sections or of the resonances that can be produced in an E plus E minus collision. And on the inside we have this epsilon 5s resonance, which is being produced by with an well collected roughly 121.4 femtobarn inverse of data, and this is the largest data set at epsilon 5s resonance. So the analysis that we have undertaken to do didn't fit to do, because this is the largest data set, and we do not have any data set to do it. So we have planned to do the analysis using this 121.4 femtobarn inverse of data. And on this plot we also have the E plus E minus continuum, so which is omnipresent. So it is also present at epsilon 1s, 2s, 3s, 4s. So we cannot get rid of them in the production process, but we will see that how to suppress those backgrounds using continuum suppression methods. And in order to discriminate between the signal and the background, we have primarily two variables, the MBC and the delta E, which is defined as such, and the start quantities are in the center of mass frame. And we, while deriving these variables, the MBC and the delta E, we take help of the constraints such that the E star beam should be equal to the E star B. B is the energy of the reconstructed B meson, and the mass of the reconstructed B meson is equal to the PDG value of the B. That again has to have acceptance, detector level acceptance as well. And then we have there's experimental challenges that we often encounter when we do neutral particles, and this is where Bell and Bell 2 can do a lot better than LHCb because of the background. At Bell we have very less background than at PP colliders. So let's move to the sixth slide number. So this is the overview of the B sub s to rho 0 pi 0, the one that I'm working on right now for my PhD thesis. So the B sub s rho 0 pi 0 is essentially an annihilation diagram, as it proceeds by annihilation Feynman diagram. So by annihilation we mean that if we have a B and S bar in the initial state, we do not have a B and S in the final state. So the B and S have completely annihilated to give a new variety of quarks. And this type of diagrams or Feynman diagrams are highly suppressed within the standard model, and so these are a good probe to look for new physics. The reasons I have already stated when I talked about the loop. So because now new particles can interact in and change the Brunson fraction, and the predictions that come from the theory, from the perturbative QCD and the QCD are stated here, roughly of the order of 10 to the power minus 6, but the QCD framework predicts it to be of the order of 10 to the power minus 8. So here we have 2 order of decimals. So we see that there is a considerable disparity among these two predictions. One is of the order of 10 to the power minus 6, while the other is 10 to the power minus 8. So only this discrepancy can be settled if we go for a search, or if we can measure the Brunson fraction, then we can at least comment that why is this difference that exists in these two predictions. And this is the first time that a Bell has undertaken this work to do, and no other previous searches have been found done on the decay channel. So we want to reach the standard model sensitivity for the decay with the Bell available Bell dataset, which is the Epsilon 5s, and we will try to put the first upper limits on the Brunson fraction for this decay. I'm on slide number 7. So these are some of the selection criteria that we need to apply. As I've already said, if we go back to slide number 5, so we have different kind of events at Epsilon 5s. Now, how do we select the target one, for example, B sub rho 0 pi 0? Apart from that, we have lots of other decay channels or lots of DD processes, continuum processes as well. So now we need to apply some selection criteria so that we select our target decay, that is B sub s to rho 0 pi 0. And that is why all the selection criteria guarantee that we are selecting the real signal events from the mass of Epsilon 5s events. But we will see that it's again not the case to go for some order separation as well. And this is a Bell detector. So a lot have been spoken about the Bell detector. So I'll just skip it. And some of the properties of rho meson and decay with the invariant mass. The rho meson has a very short lifetime of 10 to the power minus 24, and the invariant mass of 770 MeV squared. So they decay primarily via strong interactions. And this is some of the diagram which shows in order to know what is the IP means the interaction point criteria that you need to pick. So this is the first selection criteria that we need to pick, that the signal events that we have chosen comes from the interaction point. So that is the first selection criteria. Similarly, we apply other selection criteria to select our signal events. Number 8, so this is the background Monte Carlo study. So we first have to go for a blind analysis. When we go for regulate those events or know those events correctly using Monte Carlo studies, and then only we unblind the data, and that is we have to take a collaboration-wide review. And when we do the Monte Carlo simulation, do the Monte Carlo study for signal and a background, we find that we have correctly picked up the rows, so 770. So we have the blue, which are the reconstructed one. That means that this is coming from random combinations. Again, when we go for, say, for example, B sub s to rho 0 pi plus pi minus pi 0, we have only the final state particles. We combine using the principle of 4 momentum conservation. So here rho 0 will decay to pi plus pi minus, which are state particles. Pi 0 will decay to gamma gamma. So at the end we have only 4 particles, pi plus pi minus gamma gamma, and we'll have to make different combinations among those particles so as to we get a rho 0, we get a pi 0, and combine rho 0 and pi 0 to get a B sub s. So from a bottom up approach. And when we plot them, we find that they peak around somewhere correct values at 770 and 135. This is for the pi zeros, this is for the rho zero, which are also called as invariant masses of pi plus and pi minus. And the red, with that the red portion that we see, these are all misreconstructed. So those we'll have to take care of that. And then we'll have delta E and MBC variable. These are the primary variables, as I've already said, to discriminate between the signal and the background. And if you look into the distribution of the delta E for the signal and the background, you see that they are completely different, and this is good for us. That is why we will be able to segregate the signal and the background. Now, these are some of the numbers which we expect. Now, if we unblind the data, then we will find that at 121.4 from Femtoborn inverse of data, we will find a UDS contribution, that is a continuum of roughly 1 lakh events, charm less than that, non-BSBS very less, and BSBS approximately in comparison to 0. And we also have to look for the non-resonant decays as well. These are another class of backgrounds that can affect our analysis. We have also seen that. And our concern is that the UDS is the dominant one. That means that if we have one signal and we have 96,305 backgrounds, which is impossible. So we'll have to somehow suppress this. And in order to suppress the UDS background, we take the help of the shapes of the signal and the background. So this has been done way back in 1970. I forgot the exact year, by Fox Wolfram. So they have studied, they have said that for the signal, the shape of the distribution will be different, and for the background, it will be to back-to-back Z-like events. So by using a neural network, the neural network is essentially a multivariate analysis where you give lots of input. Those inputs are actually observables, which discriminate between the signal and the background, and at the end we have a single variable which actually try to discriminate between the signal and the background. That is, we will put a cut or put a selection criteria on the output of the neural network, and we will have actually separated the signal from the background. And this is what we have to do essentially because of the continuum background. So this is essentially done only when we have a continuum background which is dominant. And in our case, this is the scenario. So I'm on slide number 9. So this is the neural network and 1D PDF parameterizations of the signal Monte Carlo. So the first one is the neural network output versus purity. So we see that the points, the Monte Carlo data points, falls on the diagonal. So this looks good because the more we move towards 1, the more we get the pure signals, and more we move towards -1, the purity of the signal decreases, and which is good, that because if we now apply somewhere cut around say 0.8, we will have disregarded 99% of the background and with a signal acceptance of 44%. When if we apply that cut, that selection criteria on the neural network output, we will be having an efficiency of, this is the reconstruction efficiency of 10.90, overall reconstruction efficiency of 10.90, and that misreconstruction fraction is 8.9%, which is quite comparable to the efficiency. That means that we cannot just go with the signal. We'll also have to take into account the misreconstruction, and there has to be some way in order to describe the misreconstruction fraction as well. These are signal misreconstruction fraction coming essentially because of the combinatorial background. And then we have a background, pure background coming from the UDS. So we have, after applying the selection criteria, we have 723. And with this reconstruction efficiency, we have a very, very poor expectation of the signal, 0 to 1. So probably not able to see the signal, but we will be able to put the upper limit, the first upper limit for this branching fraction, for this decay channel. And then we have done the parameterization for the MC, the truth match. That means the data are true, which we know, which we have generated, and which we know properly. These are some of the variables. One is the delta E variable, the one that I've already spoken about, MBC variable, and this is another variable, which is the neural network variable. So we also take it for PDF parameterization, and corresponding to the truth match signals, we have a misreconstruction fraction, the delta E corresponding to delta E, MBC, and N prime. And we plan to parameterize them as well. We have already parameterized them, and we'll see how this turns out. I'm on slide number 10, and so
can you speed up a little?
Yeah,
okay, you're on the summary slide.
Yes, so 1D PDF parameterization of the background Monte Carlo. So these are the backgrounds and that we have parameterized, and we are currently working on the fit model to extract the signal from the background, and this is the current the status of our work. So in future we will try to do the fit, and we'll build the fit model and try to extract the signal from the background. So the summary, we have the rare decays are important in understanding physics beyond the standard model, and the D sub S sector can be potent probes for physics with high luminosity experiments such as BEL2, and I just presented the overview of the ongoing analysis. And at the end, I shall just show in line with this year's theme from the future of science, innovation, and technology. So we have these trust areas from going to Bell and Bell 2. So these are some of the areas which Bell 2 is superior to Bell. And the highlight is that Bell 2 will collect roughly 50 times more luminosity than the Bell experiment. And hence, we will be able to more precisely determine the CKM parameters. We will be able to find go for new searches. And these are some of the thrust areas where Bell 2 will be doing better: dark matter searches, search for multiple Higgs within a standard model, search for NP both within and beyond the standard model, search for new CPV sources, and precise determination of the CKM matrix parameters. So, that's all from my side.
Okay, thank you, Jyotir May. Now let's open this talk for discussion. Yeah, Paulus.
Yeah, Jyotir May, very good presentation. Can you tell me one thing is the numbers here? What is the bound presently? What is this thing? Is there any experimental bound available on this already, or?
No, sir. There are no experimental searches that have been made on this decay channel. Only we know the estimates of the branching fraction coming from perturbative QCD and QC. This will be the first search for this decay channel.
We have not completed this yet in your analysis.
No, sir. We have not completed yet. We are on the modeling stage.
Okay. So, all right. And then can you go to that loop diagrams where B2 gamma? Yeah, no. Yes, here.
Yes.
So what kind of new physics or any charged Higgs or things like that? Is that what you?
Yes, sir. Yes. So if we look into the charge Higgs spectrum, so the charge Higgs spectrum, so for example, the BD goes to gamma have already negated that. Still, there may be some new physics, say for example, charge Higgs that can somehow affect this loop process and can change the branch. Now, this is just an example that I've picked up. But for example, if we go to the BD, in the BD sector, BD to gamma, which is still not being measured, the branch is measured yet. Shubhang is doing that. BD goes to gamma at 2. So there we have things we have not found out. There is scope that there may be some new physics that can enter this loop and can change the branching fraction.
You are looking at BD also, BD goes to gamma also.
Yes, our group, one of the team members of our group is also looking at BD gamma. So our group works on the rare decays, and I am currently working on B sub S2, phi gamma, rho 0, pi 0, pi 0, pi 0, and as well as on Bell 2. Yes.
Okay.
Right. Any more questions? If there are no more questions, then I'll close this session and hand the mic over to Angana again.
Thank you. Thank you.
Thank you, sir. So this was the last session for the day. I now request Professor Ghosh to please take over the platform and deliver the concluding remarks.
Thank you, Angana. So the session overshot by about half an hour, 35 minutes. I would like to first thank all the speakers, Shobna, Vasanto, Shobhan, Jaideep and Jyotirmoy for being here. I would like to thank the chairpersons, Paulos, Ashini and Charu. I'd also like to thank Anchor, Angana, then our tech team, Basav, Hemanta, Rupam and Mridupavan, who had set this up through Teams as well as for Facebook and YouTube Live. In fact, I was checking a few minutes back, there were like 92 views in YouTube. So good number of people have at least accessed. And finally, the organizing team who was behind all these, from designing the poster to planning, Shayan, Devashish and Perumal. So basically this year we could do it only this way. We hope that this tradition will continue, and next year we will be back once again offline with people around in a hall and eminent speakers. So thank you all, and we can close this meeting now.
Okay. Thank you, sir. So with this, we come to the end of today's celebration of National Science Day 2021. We hope you had an engaging and stimulating experience altogether. Thank you so much for being a part of this year's successful event.